All right, hello everybody. Saturday afternoon, May 15th, and I sent my kids far, far away, so we're just making videos all day. I got this brand new microphone. It's very professional. It makes my voice sound really great, and we're gonna go over some homework. We haven't gone over any homework in this entire unit on graph theory, which we're almost done with, but it's not too late. It's never too late. What are we gonna do? We're gonna go over the first homework of graph theory. When should we have gone over this? 2.5 weeks ago. It was due some kind of April 27th, something like that. And actually, this entire section, 10.1, was based on the section 10.1 from the textbook, and it was basically all just vocabulary and kind of just introducing you to a whole bunch of graphs. I gave a pretty terrible lecture, I think, on this topic. But all of these homework problems are great. Many of them are silly, tedious little mess around things, but actually just messing around is what is required to get good at graph theory, and it's a lot of actually interesting problems that happen. So without further ado, we begin. This is page 599, section 10.1, like I said. First problem, produce the underlying simple graph for the following graph. Okay, so this is basically just saying, do you know what an underlying simple graph is? Well, you have two kinds of graphs. Multigraphs and simple graphs. Simple graphs have no loops, and between any two vertices, there's either an edge between them or not. This is not a simple graph. This is a multigraph because we have, you see here that we have a loop, and also between C and D, for example, there are two edges. So what is the underlying simple graph? The underlying simple graph is a graph that you make from a multigraph, and basically you get rid of all loops, and you reduce, if there are multiple edges between two vertices, you just replace it with one edge. In other words, you can think of, so okay, let me just do it. This should really take 5 seconds. And that's just it. This is the graph. This is of course A, B, C, D, E, and F. And so basically you can think of the underlying simple graph as the graph which just is seeing, if two vertices are adjacent. Okay, that's all I have to say about that. Next, for which values of n and m are the following graphs bipartite? All right, so this entire problem was just meant to get you comfortable with the definition of bipartite, and also all these things. What are all these things? I think I assigned like all 5 of them, right? So, okay, GNM. What is GNM? This is the grid graph. Is the grid graph important? I don't know. It's probably kind of important. It's a nice graph to have in the back of your mind to constantly bring up as a kind of an example, a counterexample to various sorts of things you're going to think about throughout the entire unit. So it would have been really good if we had gone over this homework weeks ago. I blame Zoom School and also myself. Okay, so what does the grid graph look like? It looks like this or whatever. This is an example that I've just drawn here of G23. It's the, I believe I'm doing this right. This was something that was, I don't even think I talked about this in class, but it was in the book. It's just, yeah, man, it's just a graph that's kind of like in a grid. So here it is. Okay, so now the question is, I think this is pretty generic. The question is this graph bipartite? And the answer is just yes, right? So, in fact, every grid graph is bipartite. You can color this vertex blue, say, and then this is one way of thinking about the bipartite graphs, is that the graphs which you can color the vertices using just 2 colors, such that adjacent vertices have different colors. So you make the first one blue, and then you make all the vertices adjacent with that blue vertex red, and then you make all the vertices that are adjacent with the red ones blue, and etc., etc. And there's nothing special, I think, about the specific number of vertices in the grid graph. You're always just going to have that same kind of situation where you can just let this be red and blue. So therefore, I'm tempted to say, every grid graph is bipartite. And you can even basically articulate the bipartition, I suppose, if you want to establish some kind of coordinate system where, I don't know how you want to do this. You want to make that like 0, 0, and then that's like 1, 0, or some crap like that. I don't know why I chose to start up in the top left-hand corner. But anyway, when the sum of the coordinates is even, based on the way I've done it here, you will have it will be in one part of the partition, one set of the bipartition, and when the sum of the coordinates is odd, it will be the other one. So that actually explains the coloration. Okay, so my initial answer to for what the values of n and m are the following graphs bipartite is all of them. Now, if you want to get kind of like weird or something, you might talk about like G21, which is just this. Is that graph bipartite? Yes. And now, I mean, you know, I think I did have some year where some people came at me with these kind of trivial special cases, but like, yo, G11, that's just like a stupid graph, and I just refuse to talk about it. So that's just not even a grid graph, man. That's just a graph with a single vertex and no edges. So I don't want to talk about that. But if that occurred to you, then, you know, so be it. Okay, that was part A. Let's do part B. Woo! What's part B? Part B is k sub n. So that's the complete graph of size n. So for what values of k and n are the following graphs bipartite? Here I want to say, like, never, right? Once again, we can draw sort of K3. What is K3? It's the complete graph with 3 vertices. What's K4? It's the complete graph with 4 vertices, K5, etc. So in all of these graphs, you know, it's just not bipartite because you can't, if you make one of these vertices blue, then you make this one red, then there's just nothing to make this one. You can't make it blue or red. And so this graph is just simply not bipartite. And this graph is even kind of, you know, less bipartite or something, because now there's no color left for this vertex or this vertex. Okay, and so the only way you might so what's the answer to this part B? I suppose. We should consider K2, which is kind of worth mentioning, I guess. What is K2? It's the complete graph with 2 vertices. Kind of dumb, but if there are only 2 vertices, then the only thing you can do is just put the edge between them. So this will be bipartite. So not even bothering to write down my answer, I'm just going to say out loud that okay. The answer to part A was for any n and m, the grid graph will be bipartite, except n equals 1 and m equals 1. My answer to part B is for n equals 2, it will be bipartite, but for any n greater than or equal to 2, no. I mean, I guess I should just write all this crap down, right? So for n equal to 2, you know, the answer is yes. But for n greater than 2, the answer is no. And here, okay, moving on. Part C. Part C says, let me just space myself out here a little bit. In parts C, D, and E, we are going to consider star graphs, cycle graphs, and wheel graphs. All right, let's do it. What is S sub n? That is the star graph. And I believe Gossett defines this a little bit controversial. I think like Wikipedia like disagrees with him or something like that. But I'm definitely looking at his picture on page 597 and make sure I'm not being dumb. No, I'm not. His graph of Sn is a graph with n vertices. So for example, taking like S5 is the so-called star graph. It's the graph where there's one vertex which is connected to every other vertex, and there are no other edges whatsoever. That would be an example of S5. And so, okay, what's the conclusion? Is this bipartite? Yes. In fact, the conclusion here is that every single star graph is bipartite because yeah, you just let the vertex in the center of the star be one color, and then you can color all the vertices with the other color. All right, D, the cycle graph. Okay, this one's kind of exciting. Let's look at 2 cases. You know, sort of C4 and C5, and I think this kind of explains a little bit what's going on here. Well, the cycle graph is just the graph with n vertices and n edges, and every vertex has degree 2. Okay, so is this bipartite? Well, yeah, this one is, because you can color every other. So just start at one vertex, give it some certain color, and then just kind of go around swapping colors. And because you have an even number of vertices, it's all going to match up perfectly. And whereas if you try to do that over here, you're going to get blue, red, blue, and then you're stuck, right? There's just no way to finish this off. And so the answer to part D is that the cycle graph is bipartite when n is even, but not when n is odd. I guess I'll write that down for my answer to part. So my answer to here is always. So n. What am I trying to say? For what values of n? So all of them. And here I'll say that if n is even, then the answer is yes. But if n is odd, the answer is no. That's my answer to part D. Okay, and finally, part E, the wheel graph. What is the wheel graph? The wheel graph is, yeah, so once again we have n, wait. Oh, the wheel graph is just a star graph, but now also with vertices. So W5, I guess, is something like this. And let me, I guess the answer to this is it's going to be never bipartite. Hold on, I need to think about this for a second. Yeah, it's just going to be never. So this is n is just going to be never, because there's just too much going on, right? This is a wheel graph is just a cycle graph with a, well, it's a kind of a combination of the cycle graph and the star graph. And so if you make this red and you make this like blue or something, and you make this blue, well, then this vertex in the middle has to be connected to every other vertex. I mean, another way of thinking about it is, suppose it's bipartite, or suppose you think it's bipartite. Well, then, okay, so there's a partition into two sets. Well, the vertex in the middle that's adjacent to the other n-1 vertices, well, that has to be in one of the parts of the partition, so put it in there. Well, then it's adjacent to every other vertex. So therefore, all the other vertices of this graph have to be in the other part of the bipartition. But that's impossible because these are all connected to each other. So that's kind of a proof that this is never the case. Okay, that was actually really fun and not so easy. It was kind of easy, but it wasn't that easy. I'm glad we went over it 2 weeks later. Draw each of the following complement graphs. Okay, so this is just more practice. What is S5? It's the graph that's in the shape of a star with 5 vertices. And so I will now kind of like, graph it or whatever. That's the star graph. So now what is the complement? Well, the complement is just the graph with all of, well, it's the complement graph. It's the graph where for every 2 vertices, there is an edge between them in the complement when there's no edge between them in the original graph. This is a concept that only makes sense for simple graphs. So, okay, so what do? We just do this, man. We just go jump, jump, jump. And then, like, what am I going to do? Like, yeah. Sorry, zoned out for a second. I guess this is just going to be like this or something. Yeah, there it is. Okay, that actually did take me a second. So, yeah, you have 5 vertices. But this actually like looks crappy enough that I'm considering just redrawing it now. So because what we really have is this situation. I have these 5 vertices. The 4 vertices on the outside of the star are not connected to each other at all. So in the complement graph, they're completely connected to each other. And so we have kind of, all right, we have, oh man, we have kind of like this, we have kind of like a K4. But then there's also this extra vertex that's in the middle. Well, that extra vertex in the middle, which had degree 4, now has degree 0 because it was in the original graph connected to every vertex. Now it's connected to no vertices. And so that's pretty much it. And yeah, interesting. Okay, more things to say about that, but moving on. I mean, basically, if you sort of add every edge that's in the original. So that means I should sort of erase these because that's just distracting. But if you add every edge that's in the original graph and every edge that's in the complement, if you sort of superimpose a graph and its complement, which is kind of what I had already, then in fact what you get is just the complete graph, right? So the complete graph is kind of okay. So and that is indeed what you get, right? Every vertex has degree 5 if you add its degree in this graph and also in this graph. Okay, more. Draw the complement graphs for each of the following 3 graphs. So now I'm convinced that maybe it's a bad idea to just draw it in the spot, but I don't know. Too late. How do I do this? This could get kind of ugly, right? Let's see. E is going to be connected to everything because it was connected to nothing. Shoop. Shoop. So, and then C had a degree 2, but now, well, basically, look, you have 1, 2, 3, 4, you have 7 vertices. So every vertex is now got to have degree 6 because we're basically just making the complete graph. So 1, 2, 3, and then it's just got to go here, 4, 5, and like arbitrarily, I will do that for 6. And then same, right? Am I done? No. This one is got to go 3, and then 4, 5, and now, was there no other way to do this? B is going to go to A, D is going to go to A rather, and D is also going to go to G. So now I think every vertex has degree 6. I guess I'm still missing some, man. Oh yeah, because B goes to E. 1, 2, 3. Oh, this is terrible. Wait, this is like actually legit terrible. And A goes to G. So actually, I really can barely tell what the hell is going on there. So that's actually just terrible. What does he do in the back of the book? I don't think I've ever done this problem before. Wasting time, bad video, bad video. I'm wondering if he just has some sort of elegant picture, or does he just kind of refuse to do this one? Yeah, it just looks terrible. It just looks terrible in the back of the book also. But I don't care enough to redraw that. Okay, I mean, do I? No, I don't. I mean, I think it's all right now, right? Because every vertex has degree 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 1. Oh, I did find a mistake. G and D were already connected. Hold on. Man, I want to at least be right if I'm not being efficient. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. What am I missing? F to D? Yeah. F to D, A to D. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, yeah. All right, that's right now, but it looks terrible. All right, I hate this problem. Draw the complement graph for this graph. I also kind of don't want to do this. Once again, I need to do like, well, now I'm just going to make the complete graph. At least this one's a little bit more kind of symmetrical. So, and now am I done? I guess I'm just done now, right? Because every vertex has degree 6. So every vertex in this graph did have degree 2. So every vertex in the complement graph is going to have degree 3. And together, if you superimpose them, you just get K6. That's K6. All right. Woo! For what values of n and m are the following graphs regular? What does it mean for a graph to be regular? It means that every vertex is the same degree. Well, Kn, I guess, is just always regular, right? That's just what Kn is. So if you draw sort of K4 and K5, well, every complete graph is going to be regular. In fact, the degree of Kn is going to be n minus 1. Every vertex is going to have degree n minus 1. So for what values of n are the following graphs? All of them. And S sub n, when is that going to be regular? I guess it's like never or something. S2 maybe. If you give me like S, 6, What is S6? Just to remind you, it's the star graph with 6 vertices. So that's like that. Well, here the vertex in the center is going to have degree n minus 1, 5, but all the other ones are going to have degree 1. In fact, you can sort of define the star graph as the graph where the star graph with n vertices as the graph where n minus 1 of the n vertices have degree 1, and one vertex has degree n minus 1. Therefore, from this technical definition, we can sort of see that there will be one case. It will be true only when n minus 1 equals 1, which is to say when n is 2. So when n is 2, that's the star graph S2. Kind of dumb because it means there are 2 vertices only, but this one was so. So here it will be regular, but that's it. Yeah, good. So only when n is 2, and here my answer is always. Okay, so these were all just like fun little warm-up problems, almost like middle school kind of thinking, pattern recognition, sort of the fun part of math, the fun part of graph theory. Now we're getting into a little bit more, it's getting a little bit more theoretical, but still sort of like anyone can do this. It's discrete math. It requires no background, just common sense. How many edges does the complete graph have? Prove your result. Okay, this is just a thing that's already come up in this class like 5 times. So this is not new, but we were supposed to learn this on like the first day of graph theory by doing this homework. So maybe you did the homework and took it seriously and got the problem right, and therefore you did learn it. How many do we have? Well, look. I mean, you can just count them, right? Here are here's a graph with 5 vertices. This is K5, and so yeah, how many total edges do we have? Well, you can, the super lame way to do this would be to go here and be like, okay, that's 4 edges, cha, and okay, let's just actually do this. So that's 4 edges, and then we pick a new color. We go over here to this next. How many here? Well, 3 that haven't already been accounted for, and then we go over here and we're like, oh, 2 that haven't already been accounted for, and then we go over here and we get 1. So actually, this is nice kind of casual proof that in fact the total number of edges in Kn is going to be 1 plus 2 plus 3 plus all the way up to n minus 1. And this we know because we know the formula for the sum of these numbers is going to be n minus 1 over 2. So that's one way of doing it. Another way of doing it is to that's I think a little bit more principled, is to just more abstractly now, if we have a graph with n vertices, then well, how many possible edges? Well, the complete graph has every possible edge. Well, how many possible edges can there be? Well, for every 2 vertices, there is an edge. So just how many pairs of vertices are there? Well, there are n choose 2 pairs of vertices. So I did this in class 2 weeks ago, but I'll just say it again, right? N choose 2 counts the number of ways from among a set of n objects of choosing 2 of them. Well, there are n choose 2 ways of choosing 2 vertices from a set of n vertices, and for every pair of vertices there is an edge between them. Thus there are n choose 2 edges. Of course, n choose 2 is just n minus 1 over 2. So that's kind of like a nice happy fact there, right? That we've proven. There was like another thing I wanted to do. I thought I was going to do something cooler there, but maybe not. This is kind of just like a proof that, yeah, I guess this is kind of interesting, right? Because this is like the n minus first triangular number or something like that. This is kind of like what we've almost just done in some ways is a combinatorial proof that 1 plus 2 plus 3 plus n minus 1 is n choose 2. So that's maybe like independently interesting or something. Anyway, how many edges does the complete bipartite graph KNM have? Well, now, what is the complete bipartite graph KNM? Well, it's the one in which we have, a certain number of vertices, n of them, say, in one part in one part of the partition, and in the other part of the partition we have m vertices, and it's bipartite, but in fact it is a complete bipartite in the sense that for every possible edge exists. Okay, well, how many total edges are there then? Well, it's just kind of a simple counting argument, right? You go to each one of the m vertices, and it has an edge with each of the n vertices in the other partition, and therefore the answer is mn. Okay, I think that's pretty simple, but still, some counting principles are at play here. Okay, good. Now we get really more something like a math problem. Prove that no graph can have an odd number of vertices with odd degree. Okay, this is kind of maybe extremely obvious, but maybe not. I don't know. So this is basically an application of the handshake lemma. What is the handshake lemma? It says that if you have a graph and you take the sum of the degrees of all the vertices in that graph, then let's just keep it vague. Then what you get is twice the number of edges. Okay, this is of course makes complete sense, because what is the degree of a vertex? The degree of a vertex is the number of edges incident with that vertex, and every edge is incident with two vertices. And so if you add up the degree, if you go vertex by vertex throughout the entire graph and look at the degree of that vertex and add them all up, then you're counting every edge exactly twice. So this is really like a combinatorial proof here is what this is, that this is true. Okay, well, keeping that in mind, then of course you can have an odd number of vertices with odd degree, because if you have an odd number of vertices with odd degree and you add them all up, then the degrees of all those vertices will be odd. But in fact, the sum of the degrees of all the vertices must be even. Now, if you want to do this a little bit more carefully, then you have to maybe sort of say, okay, something like this, right? Like, let A be the set of vertices, with let A be the set of all vertices such that the degree of that vertex is odd. And then let B be the set of all vertices such that the degree of that vertex is even. Well, the degree of every vertex is either even or odd, and so this is a partition of the set of vertices into these two disjoint sets. Well, what are we supposed to be doing now? Prove that no graph can have an odd number of vertices with odd degree. So suppose so. So suppose that there is a graph with an odd number of vertices of odd degree. In other words, what we're supposing is that the size of this set A is itself, odd. But then we do the following. We ask for the sum of the degrees of all the vertices. So on the one hand, the sum of the degrees of all the vertices is twice the number of edges, but on the other hand, the sum of the degrees of all the vertices is just the sum of the degrees of all the vertices in A plus the sum of the degrees of all the vertices in B. So I don't know, I'll just do something like that. I in A, I in B. Well, if A has an odd number of, this is going into way too much detail, but if this is kind of the problem right here, right? That if A has an odd number of things in it, then what are you doing here? You end up adding up. Oh my gosh, how do I say this? The degree of every A is the set of all the vertices with odd degree. I'm adding up all those degrees, so I'm adding up an odd number of odd numbers. If you add up an odd number of odd numbers, fact of number theory, like that's just odd. And if you add up all these vertices have even degree. So regardless of how many vertices there are here, this is going to be an even number. This is like the totally formal way of doing this. So one more time. If you had an odd number of vertices of odd degree, then by taking all the vertices of even degree and adding up all their degrees, that's even. But if you had an odd number of vertices of odd degree, then if you add them all up, you're adding up an odd number of odd numbers, which is odd. But therefore, the degree of all the vertices would be an odd number plus an even number, which is odd. But that can't be, because by handshake, the sum of the degrees of all the vertices is even. So this is a contradiction, and that's pretty much that. All right, that was too much detail, but maybe just enough for one person out there on the internet. 9 is just an application now, right? So that's actually kind of a powerful, maybe that's a powerful thing to know. Okay, suppose you use a regular graph in which every vertex has odd degree k. Okay, this is kind of interesting. This means that we have a certain number of vertices in this graph. These are regulars. Okay, so suppose we have n vertices in this graph. The graph is regular, so the degree of every vertex in this graph is k, so we say, and also that k is odd. Okay, that's just the setup of the problem. Every vertex is odd degree k. Prove that the number of edges in G is a multiple of k. Let's count the number of edges. How do we do it? Well, by handshake, the sum of the degrees of all the vertices is twice the number of edges. But also, the sum of the degrees of all the vertices is just the number of vertices, n, times the degree of each vertex, which is k, since it's regular. Okay, so I get this nice kind of relationship here. But now, by the previous problem, what can I say about n? Well, n must be even. N must be even because you just can't have an odd number of vertices of odd degree. So if every vertex has odd degree, then there must be an even number of vertices. And so since n is even, we may divide both sides by 2, knowing that n over 2 is an integer. This is maybe the simplest thing to do. And since this is an integer, now what are we trying to do? Prove that the number of edges is a multiple of k. Well, there it is. We're done, right? The number of edges is a multiple of k. K divides the number of edges. All right, this is a lot of math going on here. If you see what's going on, there's counting arguments, there's kind of combinatorial proofs, there's kind of basic symmetries, there's sort of number theory, master. So this is really the culmination of this entire unit, and this is only the very first section. All right, more. Show that if G is a simple graph with n vertices and epsilon edges, then epsilon is less than or equal to n choose 2. I believe that this is a stupid problem because, hold on a second. Show that if G is a simple graph with n vertices and epsilon edges, then epsilon is less than or equal to, well, I mean, yeah, suppose we have n vertices. The simple graph with the most possible number of edges would be just kn, and kn just has n choose 2 edges. So that's all I have to say about that. So I think this is kind of a silly problem, right? The complete graph has n choose 2 the complete graph with n vertices is n choose 2 edges. So every other graph is going to have that many or less. I think that's really all there is to say about that. Okay, let G be a simple graph with n vertices and epsilon edges. How many edges are there in G complement? Once again, I kind of like covered this already, in the earlier problems. I guess I was supposed to be discovering this fact, but I knew it already. That if the complete graph has n choose 2 vertices, and so G has n vertices and epsilon edges. Well, then G complement will have n choose 2 minus epsilon edges. So that's just all there is, right? Because take a graph with n vertices, and what's the complement? The complement is the graph where there's an edge between 2 vertices if there wasn't before. So together, all the edges in G and all the edges in G complement combine to make the complete graph, which has n choose 2 edges. So I think that's pretty easy. All right, moving right along here. 14 says, if G has 10 edges and G complement has 5 edges, how many vertices does G have? So this is just an application of what we just proved, right? Interesting. No, this is a little bit interesting. G has 10 edges, G complement has 5 edges. So if I add up the number of edges in G and the number of edges in G complement, I get 15. Therefore, what does that tell me about G? Well, it just so happens that 15 just is, let me not mess this up, like 6 choose 2, I guess. Yeah, that's just true, right? 15 just is 6 choose 2. So, was there a more principled way to do that? I guess the more principled way, besides just doing it, would be to say that n choose 2 is, I mean, this is kind of lame, but right, n choose 2 is n factorial over n minus 2 factorial 2 factorial. I even skipped this explanation earlier because I thought it was kind of beneath us. But what is this? It's n minus 1 over 2. And so, since that's just the formula for n choose 2, then really what we're doing is we're sort of solving this equation. Like, by the theorem from the previous slide, the number of edges in G plus the number of edges in G complement must be the number of edges in some complete graph. And so now we're simply trying to figure out, which complete graph it is. I just did some quick, like, guess and check or something, or just applied known memorized facts to know that this must be 6. But if you didn't want to do that or something, you could just, like, solve this equation by figuring out, hey, which number n is it such that n choose 2 is 15? This is, like, pretty lame, I suppose, but you could do this, and you would find big wait for it. Oh yeah, this is like what you kind of crap used to do in pre-calc C, and n is 6, so that makes me feel good. Okay, so finally 15, which seems to be just kind of like more of the same or something. G has j edges and G complement has k edges, where okay, come on, man. So what this means is that J plus K has to be J plus K has to be so suppose G has n vertices. That's the goal, right? Of this problem number 15. Find out how many vertices it has. So let's figure out what n is. Well, if I take the number of edges in G plus the number of edges in G complement, that's J plus K, then that has to be n choose 2. This is just a fact. Well, now what is n choose 2? Well, it's n minus 1 over 2. And then just kind of mysteriously or something, they tell me, broken up into 2 lines, that 2 times j plus k has to be m plus 1. So I think this is kind of a dumb problem. So 2 j plus k, therefore, is n minus 1. But therefore, it's also true that 2j plus k is m plus 1. So that's just another way of saying that n minus 1 is m plus 1. And what am I supposed to conclude here? I guess I'm supposed to conclude here that n is, or rather, to now abandon the notation I invented, what does n have to be? N has to be like m minus 1 or something, right? So the answer here is that G has m minus 1 vertices. I actually kind of hated the way I just did that problem, because maybe a simpler thing to do would have been to not introduce n at all, and to simply just like observe or something that m plus 1 over 2 in fact just is m plus 1 choose 2. Wait, so did I just like screw this? I actually just screwed this up even. So the answer is m plus 1 vertices. Yeah, G has m plus 1 vertices because G has m plus 1 vertices because in fact it is m plus 1 choose 2, which is m plus 1 times m choose 2. Yeah, so okay, great. That was a little bit embarrassing. Okay, a couple more left. This is a very interesting problem. This is a famous problem of graph theory. You can't do even a short unit on graph theory without encountering this problem. Let G be a simple graph with at least 2 vertices. Prove that there must exist 2 vertices in G that have the same degree. This sounds incredibly much like a situation in which we are going to be using the pigeonhole principle, and it really is. In fact, this exact problem, rephrased not as a problem about graph theory, but as a problem about something else. I've put this before on the test, the live test on the pigeonhole principle unit, because this is kind of one of the classic applications of the pigeonhole principle. Well, if we think of graphs as friendships, then what this is saying is, I got a lot of people, n people. So suppose I have n people. Suppose we're at school or something like that, and there are n people in the school. Prove that there must exist two vertices in G that have the same degree. This can be rephrased as, prove that there are two people, with the same number of friends. Another way of thinking about this is a whole bunch of people, 100 people, all enter into a big room and engage in 20 minutes of just like rampant high-fiving, where some people high-five with a lot of people and some people high-five with no one, perhaps. And the question when we're all done is, claim two people must have done high-fives with the same number of people. Okay, so this is kind of the same thing. And this is sort of not immediately so obvious how to do this problem, actually, because, okay, let's think about it. If you suspect that some sort of, so we just ask this kind of innocent question now. Could everybody, let's go back to friendship, n people, like in school, and could everybody in the school be friends with a different number of people? Well, how many different people can you be friends with? Assuming this is a simple graph, so you're not friends with yourself, what are the kinds of friendships you can have? Well, you can be friends with no one. So you can have no friends. You can be friends with just one person. You can be friends with two people. You can be friends with three people, all the way up to the most number of people that you can be friends with is everyone else. So that's n minus 1. So this is a total of n. In other words, there are n possible numbers of different kinds of friends you could have, different numbers of friendships you could have. So if there are n people and there are also n different numbers of friendships that you could have, then at first it seems that maybe this is possible. But there's a subtlety. The subtlety is, can you really have someone that's friends with no one, and someone that's friends with just one person, and someone that's friends with just two people, all the way up to someone that's friends with everyone else except themselves? No, you can't, because it's impossible to have a vertex of degree 0 and also a vertex of degree n minus 1. If you think of this in terms of friendship, the way I've taught this problem before is like, suppose you have some go-getter who's a very happy, positive person, and they write in their journal or whatever at the beginning of the year, I'm going to be friends with every single person in the entire school. So you have n minus 1 people that you need to befriend. And that's actually very interesting. Huh. Whoa. Very interesting. Depending on, when I use the eraser, whoa. Okay, hold on. Things are getting crazy. Whoa. Okay, anyway, never mind. So anyway, well, if that person, so great. Suppose that's something you want to do. Well, someone else writes in their journal at the beginning of the year, my goal is to be friends with no one. I want to make no friends. Okay, well, this person is like the very friendly person. This is the like misanthrope. Well, one of them is going to lose, right? This is like a heartwarming movie. Either the happy person will melt their cruel heart and they will become friends, or the misanthrope shall win and this person will just, not make all the friendships with everyone in the school. Okay, point is that there's some casework involved here. So case 1, there is a misanthrope. So case 1, G has a vertex of degree. Oh my gosh. Case 1. Case 1. G has a vertex of degree 0. If G has a vertex of degree 0, then there is a vertex that is not adjacent to any other vertex. And so then the sort of max degree of any other vertex is n minus 2. Because given some arbitrary vertex now, you're not friends with yourself because the graph is simple, and therefore there are n minus 1 other vertices which you could potentially be friends with, but you're simply not adjacent to this vertex of degree 0, and therefore at most you can be adjacent with n minus 2 other vertices. And so the possible degrees are 0, 1, 2, all the way up to n minus 2. Okay, what's case 2? Case 2 is G does not have a vertex of degree 0. Well, then, what are the possible degrees now? Possible degrees are 1, 2, 3, all the way up to n minus 1. But in both cases now, we have sort of like, here we have n minus 1 possible, and here we have also n minus 1 possible. So in both cases, I don't really feel like writing this. In both cases, we have n minus 1. I'll just write, so the conclusion is there are n minus 1 possible degrees, but n vertices. And so now the vertices are the pigeons, the n vertices are the pigeons, and the n minus 1 possible degrees are the pigeonholes. So by the pigeonhole principle, 2 vertices with the same degree. 2 vertices with the same degree. Because there are only n minus 1 possible degrees, but there are n vertices. So that was kind of a great problem. You can think of this as a basic problem of graph theory, but really it's kind of a pigeonhole principle problem. If you stop talking about graph theory and just talk about friendships, then it would be completely appropriate to solve this problem back in that unit, I think. Okay, good. A couple more. This one we kind of already covered. I actually forgot that I even assigned this problem. Prove that the cycle graph is bipartite if and only if n is even. Okay, I basically just don't want to do this, but okay, if we're really going to do this, 18a, because this has been sort of covered already, right? So what is the cycle graph? The cycle graph looks like this, and so I'll just leave it open as to whether there are an odd number of vertices or even number of vertices. Well, no, maybe I won't. Maybe I'll just do both cases. So let's just kind of talk it out, even though this was sort of already covered. So let's first go from bipartite if and only if n is even. So let's first go from bipartite to even. Well, if it's bipartite, then okay, then this vertex is one color and this vertex is another, and this vertex is one color, and this vertex is another, and so it just has to be even. That's a terrible proof, but the thing is I gave a very rigorous proof of this back on a graph is bipartite if and only if there are no odd cycles day, so I just don't feel like descending into the rigor once again, but you can, if you really want to, prove that n must be even. How? This is even easier than that because, well, it's actually the same thing, right? You prove it's even. How? Well, because suppose it's odd. Well, if it's odd and it's bipartite, then you begin with one vertex and you put it in one set of the bipartition. You have two sets A and B of the bipartition, and you put the first vertex in one set, and so maybe then the vertex which is adjacent to it in the cycle must be in the other set, and you keep alternating every other one such that whether or not you are in one set A or set B, in other words, whether you're to be colored blue or red, depends on the sort of length of the walk from this arbitrary first vertex that you're in. And, if n were odd, then you would get a contradiction. And so, okay, I think I'm just going to stop literally this entire problem because we did it all already. This was kind of meant to be almost sort of a warm-up to that. Of course, the other direction, going from even to bipartite, is, I think, more straightforward because here you just produce the bipartition, as I have done, right? You just arbitrarily designate a vertex in one segment and you just go around and it just works. And so you've shown that it is bipartite. And then and then part B is essentially half of. Okay, so part A is all of this was good preparatory work actually for that day where we just did it in general. But part A says if you just actually are the cycle graph, then if you're even, you're bipartite, and if you're odd, you're not bipartite. But then part B gets into, well, now I'm not saying that you are the cycle graph, I'm just talking about that you have a cycle in you. And what B is essentially the easy half of the proof, right? B says if you're bipartite, then you have no odd cycles. Then no odd cycles. And this is also, we also just already did this, right? If you're bipartite and how do you prove that there are no odd cycles? You suppose that there is an odd cycle and you just repeat the logic from above. The hard part of this proof, which Gossett does not ask, or the hard thing that Gossett does not ask you to do, is to prove the converse of 18b. The converse of 18b is that if there are no odd cycles, it's bipartite. That's what we did in class. It took us a whole hour, so I'm not going to go back to that now. All right. Last problem. Introduces more vocabulary. What's a clique? Apparently, some people say clique, some people say clique. Maybe it's like a French thing to say clique, but I think at least some graph theory people say clique. I think I'm just going to say clique. A clique in a graph is a subset such that every pair of vertices in C is joined by an edge. Okay, so what does that mean? That means it's like you have a subgraph of you which is complete. So this would be an example of a clique. Choop. Okay, an independent set in a graph is a subset such that no pair of vertices is joined. So now, if if you have a class, then a clique is a set of people and they're all friends with each other. That's why we call it a clique. Or I don't know the etymology exactly, but I think so. An independent set is a bunch of people in class such that no one is friends with anyone else. So this is like suddenly you're in a breakout room and you're just like with 4 people and actually none of you know each other or none of you are friends with each other, let's say. So that might look, well, it's going to look like this in fact. But the thing is there might be other things going on out here, right? Like you might have it doesn't mean that these people have no friends. It just means that they're not friends with each other. So I think that explains that pretty well. Okay, and now we have some follow-up kind of questions or whatever on this. Okay, A. So let G be a simple graph with n vertices and suppose that G contains an independent set of size k. What is an upper bound on the number of edges in G? All right, so n vertices. But then there are k of them in which they are not related to each other at all. So how many edges could we have at most? Well, I guess, to think about this for a second, but I guess every other edge would be there, except for this one, except for these. So if there are k of these, but there are n vertices total, then if there are n vertices total, then the complete graph would have n choose 2 edges. And this graph, the graph with the most, so think about it like this. What does the friendship network look like in a class where there are k people that are not friends with each other, but otherwise there were the most possible number of friendships? Well, then there would be all the friendships except for these k choose 2 friendships that don't exist. So that's just the answer. The number of the the number of edges is less than or equal to this. Okay, and finally, part B just asks you to do it, man. Suppose you have a graph with 5 vertices and an independent set of size 3 that attains that upper bound. Well, this would mean that there are these 3 people that are not friends with each other. I started to pretty much draw this over here. But then there are these, let's do it a little bit differently. Then there are these 2 people which are friends with each other and also friends with all of these people. So I kind of screwed this up slightly, but that's fine. So how many edges does this graph have? 4, and it has 8, I guess. No, that's just wrong. It has 7. Is that just right? Well, 5 choose 2 minus 3 choose 2 is 10 minus 3 is 7. So yep, this is just an example of, okay. There's actually more interesting things to be said about this, but that's good enough for now. Okay, how long was this video? I don't even know, but I'm gonna stop it now. Good. Oh, 55, only just a tight 55 minutes. Okay, bye.